Mind that we have ×2 being done per glucose molecule. It takes place in the mitochondrial matrix, and it has other names as well. Some people call it the tricarboxylic acid cycle. Some people call it the citric acid cycle. I prefer to call it the Krebs cycle because we should at least be respectful to the people who fucking discovered this shit. God knows how much work went into this. Probably neglected his wife and kids. Chemically speaking, I would like to have started off at the reaction of where acetyl-CoA comes into this, but since it's a cycle and we can start anywhere that we'd like, really, pedagogically speaking, I'd like to start with citrate as it's the citric acid cycle. So there's an abbreviated, or it's not abbreviated, it's a Lewis structure for citrate. And the reason why I drew these part down here in gold is because that's the part that actually came from the acetyl-CoA, as it's the acetyl group there. So citrate is going to next react with an enzyme that's going to convert it from citrate to something called isocitrate, and the name of the enzyme is called aconitase. And in this video, because I'm just going to be doing an overview of the reactions that's happening, all that I'm really going to be showing you is the name of the enzymes, the reactants, and points of oxidation and reduction that's hopefully demonstrated by their structures. I will make another video where I talk about the specifics of each and every enzyme. But anyways, this gives us isocitrate. Here's a drawing of the structure of isocitrate. There's probably better pictures in your book if you'd like. This is all from the diagram in chapter 18 that I'm going to be going over. But anyways, isocitrate is going to be reacting with something known as isocitrate dehydrogenase and NADH+ to give us alpha-ketoglutarate. I wanted to have remembered, I think in my video that I did on specifically the 2 electron carriers, I said that whenever we have NAD+, whenever NAD+ gets reduced to NADH, the carbon compound that usually gets oxidized tend to have an increase in the amount of carbon-oxygen bonds, which that's what's happened to our isocitrate to the alpha-ketoglutarate. So you definitely want to take note of that. We also get, as other products in this reaction that we're not really interested in terms of the cycle, but are interested in terms of metabolism, CO2 and then NADH. So remember, that's what we're doing here. The whole purpose of this cycle is to make lots and lots of NADH and FADH2. So we've already made one there. That's great. Also, in case this is just review, whenever we see a dehydrogenase enzyme, we always want to be thinking about the fact that we're taking a hydrogen and we're moving it somewhere else. And the process of doing that is always going to be an oxidation reduction. I always keep in mind in the back of my head the organic chemistry definitions of oxidation and reduction, with the amount of respect to carbon-oxygen bonds or carbon-carbon bonds or carbon-hydrogen bonds. Anyways, though, alpha-ketoglutarate is going to be converted to succinyl-CoA through the use of an enzyme known as alpha-ketoglutarate dehydrogenase complex. And that's really similar to the pyruvate dehydrogenase complex. In fact, I think there's some homology between those two. We also reacted this with NADH+ and CoA. Obviously, if we're having a dehydrogenase complex, that's going to be giving us NADH. CO2, succinyl-CoA, which is the one that's really relevant with regards to the cycle. Now, succinyl-CoA is going to react with ADP and some inorganic phosphate, which I think you can imagine what we're about to do here. And it's going to be reacting with an enzyme known as succinyl-CoA synthetase to be converted into succinate and ATP. I'm not going to write it out, but what's nice about this is the other name, for some reason, and it's a less common name, but I think it tells us more about what it does. It's sometimes known as succinate thiokinase. So we're going to be making ATP. Also, just note that in some, because this is weird. We've talked about the different types of fermentation that we have. There's a lot of variation, and even in terms of how they have their electron transport chain set up as the final electron acceptor. But I don't really know of a whole lot of variation in the Krebs cycle that I can think of, other than the fact that in some contexts, instead of ATP, it's GTP, which isn't really that much of a difference. But anyways, because succinate is a completely symmetric molecule, we don't really know how to maintain which one of those which came in certain orders from the acetyl-CoA. But notice that even though in these past 2 reactions we have lost molecules of CO2, and that's the last one to leave is the one from the acetyl-CoA, and that's why acetyl-CoA is so important, is because it's what keeps, in terms of the number of carbons in the cycle, it's what keeps it going. Nextly, succinate is going to react with succinate dehydrogenase, that's a hydrogenase, my handwriting is really bad, and FAD, and this is going to give us fumarate. So FADH2, which will also be made to go off to the electron transport chain. But remember from my way back when we did the video on the electron carriers, whenever we're using FAD as a reactant for an oxidation reduction reaction, what we're really just doing is we're taking away hydrogens, which I think you can see the only places that we're going to be able to take away hydrogens from, and that's going to result in the formation of the carbon-carbon double bonds in the carbon compound that we're going to oxidize. In this context, succinate, which being converted to fumarate. So let's draw the structure of fumarate so you can see what I'm talking about. Next, we have fumarate is going to react with the enzyme known as fumarase to give us malate. Next thing we're going to do is we're going to be converting malate into oxaloacetate, and we're going to be doing this through the use of NAD+ and then malate dehydrogenase. So just before I draw the structure of oxaloacetate, we went from NAD+, we have this type of a compound that we have here. Think about what type of reactions does NAD+ do, what is it going to be doing to the carbon compound that's been oxidized, and you can probably guess what the structure is of oxaloacetate. And then the last step, which converts oxaloacetate back to citrate, well, I mean, just by looking at the number of carbons, I think you can imagine we're going to have to add 2 carbons to that, and that's going to be in the form of acetyl-CoA. Just really running out of room here. I shouldn't have probably drawn that as big as I did. But anyways, oxaloacetate reacts with water, acetyl-CoA, and citrate synthase to give us citrate. Now, acetyl-CoA, I'm going to try to draw the structure of that so you can see where those carbons came from. Okay, so let's look at, kind of just recap a little bit of what happened. And yes, I will talk about this in much more detail in my next following videos where we talk about each and every one of these enzymes and the specific roles that they play. But we have citrate, which has 1, 2, 3, 4, 5, 6 carbons. That's going to react with aconitase because it has an intermediate similar to aconitase. And we're going to convert it to isocitrate, right? We're just converted it into the isomer form, especially at the, in this context, the 2nd prime carbon, right? Which personally looks a lot more stable just looking at it to me than what we had here. But anyways, isocitrate is going to undergo some redox reactions with isocitrate dehydrogenase and NAD+ to give us NADH and CO2 as a byproduct, thus converting us to alpha-ketoglutarate. Notice that the CO2 that we lost did not originate from the acetyl-CoA, right? That was the new one. That's the first one we just put on there. That's going to be the last one to leave, and then it's this kind of build up as a cycle here. So alpha-ketoglutarate is a product that we get, and then it's going to react with another molecule of NAD+ and some coenzyme A, along with the alpha-ketoglutarate dehydrogenase complex. This is functionally and structurally very similar to the pyruvate dehydrogenase complex, and that we have decarboxylation happening and then ultimately oxidation and reduction. This is going to have an NAD+. Noticing the number of carbons, we now have 1, 2, 3, 4, 5 carbons in this molecule because we lost one there. And we're going to be converting it to succinyl-CoA, NADH, and CO2. So we've lost yet another carbon. So now we have 1, 2, 3, 4 carbons, and then a thioester bond, which I want you to think whenever you see a thioester bond, think about energy. That has as much energy in a thioester bond as, or at least the hydrolysis of it, as ATP. That's very interesting to me. But anyways, through the succinyl-CoA synthetase, or sometimes called thiol kinase, which I think is a better name for it, it gets converted into succinate, ATP, and coenzyme A by the hydrolysis of that reaction. So we're going to use that to make ATP. Now, in some contexts, this can be GTP, but, you know, an energy transfer molecule that usually is a nucleotide triphosphate. Anyways, succinate is a completely symmetric molecule at this point. We don't really know where the carbon atoms were that came from acetyl-CoA, but we know that they weren't removed by the 2 carboxylation steps at the beginning. Succinate is then going to react with succinate dehydrogenase, because there's a whole lot of oxidation reactions and reduction reactions happening here, to go from FAD to give us FADH2. Whenever FAD reacts and the carbon compound that it reacts with tends to get carbon-carbon double bonds, and whenever NAD+ reacts with something, we tend to get carbon-oxygen bonds increased. So fumarase is going to then be the enzyme that fumarate reacts with to give us malate. Notice that there's really not much of a structural, I mean, there's a structural change in the two, yes, but as far as the number of carbons go, not really a whole lot has changed there. Changes in the oxidation state, however. But anyways, malate is going to react with malate dehydrogenase with NAD+ to give us oxaloacetate and NADH. So notice again that whenever we have NAD+, we have an increase in the number of carbon-oxygen bonds. Oxaloacetate is then going to react with water, acetyl-CoA, and citrate synthase, and the thioester bond of the acetyl-CoA is going to be used to hopefully restore some of the energy potential that we have in citrate so that we can keep this cycle from going and going and going and going. Now, the only other thing that I wanted to say about this was in terms of primary regulators that we have, there's only two. There is isocitrate dehydrogenase. That's one of the few primary regulators, which I will talk about this in much more detail later on. And then alpha keto glutarate dehydrogenase complex, being structurally similar to the pyruvate dehydrogenase complex, obviously can be susceptible to the energy charge of the cell and other mechanisms, which we'll mention later. But that's it for the Krebs cycle.